Hello everybody, it's Adam Hurd, 973 Ramp again, and today we are going to talk about motor curves and motor performance. The same video will not cover how to size a motor for a particular system, but I will do another video on that. First, this video is just going to focus on how a motor behaves in FRC purposes, a brushed DC motor, because that's everything that we do, and some, I don't know if misconceptions is the right word, but a different way I view things than some people view things. So first we're just looking at a motor curve. And I'm trying not to go too intense, but I'm going to try to keep it detailed enough that people understand understand what is going on. So first I'll say that a motor curve is for a given voltage. So although this curve isn't noted, it actually might be noted on one of the above pages, this is for 12 volts. And this is for the sim motor. Everyone should know the sim motor. We're going to talk about him first, just because everyone knows who he is. So a motor at a set voltage, I like to think of it essentially as a trade-off between torque and speed. With this guy at 12 volts, if you have no load on him, no torque, just the shaft's free spinning, you will hit this speed. If you lock the shaft and you get no speed, you'll hit this torque. And if the load that your system is putting on your motor is halfway, you'll be halfway there. And I said the load that your system is putting on the motor because there's a misconception isn't the right word again, but it seems like a lot of people think they control what's going on with the motor, and that's really not the case. All you control is voltage, and then the motor will try to move, and whatever torque it experiences will determine what speed it is going um, in the current draw and such. So you cannot will your motor to do anything else, but you do get some effects by using a control loop to increase or decrease voltage. But voltage is all you're controlling. You do not get to pick your point on this curve in real time for a set voltage. If you're at 12 volts, the torque that the system has experienced purely determines the speed you're at, and therefore the power and efficiency and all that stuff. So you will see, since power is torque times speed, and in metric units that comes out really nice. This is in ounce inches. Unfortunately, it'd be nice if that was in newton meters. You would convert RPM to radians a second. But at exactly half power and half torque, half speed and half torque, you get peak power because it is the product of them, and that's kind of a square pen optimization problem. Rectangle is not the maximum area a square is. But there are thermal limits that limit this. It's something we're going to get to towards the end, but I'll just briefly allude to that now. You can see this red line current increases as torque increases. So if you were to take this current times the 12 volt voltage, you would get a power graph that is linearly increasing that will actually always be above this mechanical power curve. And the reason it's always above is your mechanical output power has to be less than your electrical input power. And if that graph was shown, you would see that towards this end down here, you have huge diminishing returns. You're very inefficient. And actually, I guess this efficiency line is showing what we're talking about. So you can see that at peak power, you're already fairly inefficient compared to peak efficiency, but not horrible. But certainly as you go more and more down the torque range, we have almost no rotation, the motor becomes very inefficient. And this, for any sustained period of time, will definitely break even the Sims, sustained period of time, short period of time, no problem, and or trip your breakers. So then if you look over here at peak efficiency, which is about here, your power is not very high. So I guess, yeah, this purple line has the power units on the right, so you can see peak power on a sim. Mechanical is like 340 watts, 330, somewhere around there. And the power at peak efficiency is a little over 100 watts. Now, that the 100 watts is still a fair amount of power for doing something, but certainly 3 times power is better. Now, both because it's more efficient, I guess I'm saying that exactly, because you are operating at this high efficiency point where you're not making a bunch of heat, because that's where the electrical power that isn't going to mechanical power goes, you can operate in this range for a much longer period of time. You could easily operate the entire match here, and I don't know the exact cutoff for the sim or any other motor. I kind of have some gut feels. I just don't want to say those and lead people the wrong direction. The farther you go to the right, the lower your duty cycle must be, as in you must run that motor less per match at that operating point, or you're going to overheat it and fail it. Some teams really like to push that limit. We kind of end up doing that a lot, to where we often might be replacing motors every event, and some people might think that's crazy, But you know, if you can gear something 10 to 20% faster, and that speed advantage is actually resulting in higher performance on the field, more points, that sort of thing, then replacing motors might not be crazy for you. But certainly you don't want to be designing for that point if you don't have a good grasp on your system, because it's real easy to miss that and have something that's going to burn out the motors all the time. So I know I'm kind of rambling here, and I might not have hit all the points, but I'd like everyone to understand torque speed curve. Full torque, you have no speed. Full speed, you have no torque. Anything in between is a linear trade-off between them. And it's actually surprising how linear that line is when you measure that experimentally. It's pretty good. I think Richard Wallace did some testing and had some motor curves that would be cool to pull up, but I don't want to dig through those in the middle. But pretty good line. And so power is torque times speed. You hit peak power at your midpoint, the square optimization problem. But at peak power, you're fairly inefficient. You're making a lot of heat. That heat is what will damage your motor. At peak efficiency, at least for the sim, you're still making a fair amount of power, not making much heat. You could run there all match, but certainly if you ran up here, you could do more work. But once again, you can't do the whole match in that. So if you were just looking at this sort of thing, you would think that, you know, maybe a 550 is always better than, let's say, a bag motor, because the 550 has a much higher peak power. Uh, that's not actually a universal truth, though. The bag motor in many situations is probably the better motor to use, because if you set essentially a current limit, and we're going to jump to that in a minute, based on what I think will cause thermal failure in my motor for a certain amount of time, the bag motor will be able to sustain a higher power output for a longer period of time on the basis that it's a lot more efficient and it's got more thermal mass. Especially when you're looking at low speed, you know, like at an arm or something, or stall is what I mean actually, because you don't get any cooling advantages to the 550 if you're not moving it. So for something like a shooter where you're only operating that for a very brief amount of time, the 550 would be a better choice, because you can hit this peak power. You're only hitting it for a brief moment, and you do get more power to the system. But if you want to do something like an arm or an elevator that's going to be experiencing that high load, especially at low speed, stall essentially the whole time, the bag motor might be a better choice. So I run a little modified curve. This isn't actually the one I use. I just made this real quick, so hopefully I don't have that much mistakes, where I will come in, and so this is a classic motor curve now for full voltage for 100% stall. But let's say we kind of know from experience that we don't want to run our sim higher than 30% stall. You'll see this line actually gets truncated. Kind of what that is, although this is torque versus speed, and I have, ooh, I mixed my units, that should be speed right there. The torque is truncated. And essentially what that is it's scaled by this value. If the torque is above that value, we scale it down. Now in FRC, unless you're actually measuring current, or I think the Jaguars might do this, you can't actually control this way, so you can't in real time make this curve like you can with other types of motors, unless you are measuring current. But you can use this to view kind of power output you're getting at a arbitrary current limit you set, to see, okay, what's really the usable power out of our system. So I made this guy so you can select the motors. Let's say we're at a 550, and I know from experience maybe we don't want to be drawing more than 20 amps continuous. So I'll just get this to say 20. I'll settle for pretty close. Maybe we'll settle for a little closer. Oh, now I'm getting carried away. Cool, that's close enough, 20 amps. So you can see, I've done a bunch of math here. This is just scaled off. I mean, this is just the specs pulled from the other page. I'm sorry. So these are the specs you would get from the manufacturer. These weights may be a little off because they are what the manufacturer posted, but these are the manufacturer specs. These specs are scaled by whatever this voltage is, and some of them, the ones noted, are scaled by the current limit. So if you see, we change the voltage, stall current, stall torque, that kind of stuff changes, but we'll put this back to 12 for now. You'll see that based on this percent of stall torque, we have a current limit of about 20 amps. And once again, this is not a current limit you're controlling. It's just a way to visualize what kind of performance can I get out of a motor by not letting it go above percent stall. And in the future videos, we'll talk about how do you keep motors from getting into those realms, because for FRC, that's really more of a design thing than a control thing, because I know very few teams are actually doing current control. So then you can see stall torque is scaled off that voltage. This is the max torque by current. So this is saying that's essentially the knee on this graph, and that's this torque all the way across. And this is the free speed of the motor at that voltage. This value here is the classical peak power. That's if we actually did let this run at 50% of free speed, 50% of stall torque at that voltage. So 246 watts essentially, that's pretty powerful. However, when you look at what the actual peak power is, that's when we are at this knee exactly. Anything down here would be lesser power if you consulted this graph. Obviously, as you slide down this, you get a decrease in power. So this shows that, for a 20 amp current limit on the 550, I'm only getting 170 watts of power out there. And then this is the electrical power used. That's 12 volts times the current we're drawing. And I'm totally neglecting voltage sag and that kind of stuff here because that's the things I'm trying to prove here hold true separate from that. And the heat generated is 70 watts, which is a fair amount. Efficiency is 70%, which isn't horrible, but just throwing away 30%. And your heat per weight, and this is kind of a pseudo number. This alone doesn't prove anything. I'm not going in anywhere and saying, oh, I'm doing 145 watts a pound. That's bad or good. This varies with a lot of things. You really have to know the thermal properties of your motor and how much heat your motor can get out. But we do know is the 550s at low speed do not dissipate heat very well. Even with heat sinks, you're not going to dissipate a huge amount of heat very quickly with those motors. So I guess let's quickly note, I guess let's try to hit this performance if we can. I think we can't actually. I'll bump this current limit down a little bit. Maybe we'll do a 10 amp current limit. That's a 10 amps continuous is still fairly big out of these motors. So that would be essentially 23.5 divided by 2. There's a tool called Goal Seek that works nicely for this. Oh, divided by 100 too, I think. Yeah, to get that percentage. Okay, so 10 amp current lamp essentially. Now we have a peak power of actually only 90 watts. You can see how the power really gets punitive with your current limits. And no, I'll get to that in a video of exceptions there. So electrical power, much better. Efficiency goes up a little bit. The heat drops. So let's see if we can get 90 watts out of a bag motor, and let's look at what the heat per pound is. Because that's kind of, if you don't know anything else about the motors, at least assume the 550 and the bag can dissipate heat equally well. I think most would agree the bag is probably going to be better at dissipating heat at low speeds for like an arm or an elevator or something because probably bigger bearings, more heat being transferred through there. But I could be completely wrong. Someone would have to test that to prove. So we're going to switch to the bag motor, see if we can get this 90 watts, and we'll see what the heat per pound is when we do that. So switch to the bag. So I need to bump up this stall current. Let's go 25% maybe. 0.225. I keep messing that up. Oh, okay, that's pretty close there. So, oh, I already forgot what this heat per pound was, so we got to go back to when we had the main bots. Okay, so 60.88. Let's see if it'll let me redo everything. Oh, now I broke everything. Okay, so I'll just change it this way. And this was 0.225, I believe. All right, so you can see we're getting the same mechanical output power. The efficiency is much higher, and actually that's mostly coming from the bag motor is just a more efficient motor, and you can see that we're only making 30 watts per pound. You can see we actually are making more. It's not that we're just making less heat, we are making less heat, but it's also that this motor is heavier. And sometimes heavier motors are good. Like, aside from the fact that I don't like the 775s because of their failure with those windings burning, with the insulation failure, the fact that it is essentially comparable power to the 550 at twice the mass makes it a much more durable motor. So kind of what we just proved here, and I think some people may take a couple peeks at this video before they really believe me, because there's a lot of math here that I really skipped, is that a more efficient motor with more weight and, although that's not shown, the ability to dissipate heat better, which I feel like the bag would probably dissipate heat better than the 550, can sustain a higher or comparable, so can sustain a comparable power outlet with less heat made, or it can sustain a higher power outlet with the same heat made. And essentially there's going to be some number in watts per pound for each motor that would have to be tested that would tell you whether or not a motor will fail. So one thing that does change here, though, is what time period we're concerned with. And I'm not stating any hard facts here because I don't have data, but the shorter the time period, the higher this current limit can be, and the more likely the motor is to survive. Because obviously, even though we are arbitrarily setting these current limits, the motor is going to be at stall when you first turn it on and go 12 volts. So you're going to pass through higher current areas for brief times, but your operating point where you're spending most of your time is going to be in this range, or at that range if you really understand your system well and characterize it nicely. So for things that need to be held up for a while, though, this becomes more and more important. You know, if you have an arm that does not hold itself up due to friction or a gas spring or something like that, and you're always drawing some current, you need to make sure you're not going to cook your motor. And that's about everything I wanted to cover here. So I'm going to lead this into a video where we are actually going to look at both an arm and an elevator and pick gear ratios and pick motors based on this arbitrary number. So I hope everyone took away from this the rough concept of a motor and how torque and speed are trade-offs. And although if I didn't say it earlier, I'm going to sneak it in now. These graphs scale by voltage, roughly, or close enough for FC purposes. So at 6 volts, everything would scale down by 1/2. At 3 volts, it would scale down by 1/4, and that's coming from voltage divided by voltage. So 3 divided by 12 is 1/4. And that is kind of shown here, but not great. And that also what is by spec a more powerful motor might not always be the best answer for your system. Certainly anything that's operating for really brief amounts of time, or pretty much always operating near free speed or peak efficiency, the higher power motor could be a better option. But for things that you might be experiencing failure due to higher load on and more sustained stall, the lower power motor and or the more efficient motor, I guess, and or the motor with more mass and better ability to dissipate heat could be the better option. I'm pretty confident in the statement I'm making that certainly near stall, if someone were to dyno this, and even kind of out away from stall but not near free speed, the bag motor is going to whoop the 550 in most cases, even though spec-wise the bag motor is way weaker. What is the max power on a bag motor? I guess I don't have that in here. We'll add that real quick. Max power watts, and that is the 0.25. That drops out because it's half of these two values I'm going to multiply, or half squared, times that, times the free speed. Got to turn that to radians a second though, so you can divide by 60 times 2 times pi. Cool, so these numbers are correct then. So you can see the bag motor has a peak power of 147 watts essentially, and the BaneBot's 550 has a peak power of 246 watts. And although we didn't talk about this, applying the logic that we just looked at on the basis that this has big bearings, I mean much bigger bearings in this than smaller motors, this has a lot of weight, and this power output is not much less than that, the mini sim is certainly going to whoop both the bag and the 550 in terms of the ability to sustain a power output. And then obviously you can come up and do the same thing with the sim. Although I've never actually compared. It's possible the mini sim is slightly better than the sim, but that could go either way. All right, so I hope everyone learned something from this. I'm going to do another video that does arm and elevator like I talked about. All right, thanks for your time, everybody.